I like because it makes sense to me and it made sense to all the subsequent or the previous classes, so I stuck with it. So resonance, electronegativity, I'm just gonna put E in, and size. Right, so these are the 5 factors that affect pKa, right? The pKa of any acid is roughly based on the conjugate base stability. Right, so when you see it, an acid, and it has a low pKa, normally what that means is that when you pull off the proton of that acid, and it's got a negative charge there. For most acids, you're going to have a negative charge on the atom where the proton was. That negative charge needs to be stabilized by something, right? So for any acid, let's just say, right, where this is the acid. If I lose this proton by bringing in the base, electron there. If I take that proton off and I give those electrons back to X, right? This is the conjugate base. And this is what matters. This is what will tell me if the acid is going to be a strong acid or a weak acid. So if it's more stable, that means that proton is going to come off readily. So it's going to be a stronger acid. If it's less stable, opposite is true. Right? So let's take our 2 acids from up top and compare them. So we had propionic acid, which was and then we had phenylacetic acid, which was, I'm gonna write them out in skeletal form, if that's okay. And this was 4.28 pKa. And this was 4.87. Right? Not much difference, but enough of a difference. One of them, we calculated it. It was 4 times, the phenylacetic acid is 4 times stronger than propionic acid. And in chemistry, when you think about the fact that you're working on a molecular level, even subtle changes cause drastic differences in acidity or basicity or nucleophilicity or electrophilicity. Subtle changes on a molecular level are huge, right? You're talking about working on a nanoscale or in between the nano and the micro. So that matters. So about the conjugate base for each one of these, let me see, let me just move that so I can have room. The conjugate base is going to look like this. When I remove this this is the proton I'm taking off. That's very important as we study in pKa, is to be able to recognize where your acidic proton is. It's normally attached to a highly electronegative atom, right? Sometimes it'll be on a carbon, sometimes, but for the most part, your acidic proton is usually attached to a highly electronegative atom. Right. So it's not any of these other hydrogens that are on those carbons. They're less acidic than this one on purpose. right? So here, the conjugate base looks like this. What's going on out there? And then over here, the conjugate base looks like this. So now these are my two conjugate bases. When I'm comparing them, I'm comparing them based on these factors. What's the hybridization state of the atom? Can it do resonance? What's the electronegativity of the atom? How big is the atom? And is there some electronegative atom close by that can cause induction? Right? So for hybridization, remember this was what? If it's sp3, sp2, or sp. We're going to talk about that because the hybridization state actually does matter. We'll talk about it when we get to an example where it's relevant. I'll introduce you to that idea of S character or percent S character. It's in the video, but I'll introduce it anyway. And then induction is you ask the question, are there any electronegative atoms or functional groups close by? Resonance is obvious. Can I move electrons? Let me not say that. Let me not say move. Let me just say, can I delocalize electrons? Right, so hybridization, induction, resonance. How electronegative is the atom where the proton was? That's what we mean when we ask about electronegativity. Right, how electron is it? If it's highly electronegative, 9 times out of 10, the charge is going to be more stable than if it's not. Right, and then for size, that's obvious, right? How large is the atom? So we're asking this, and I want to clarify this up front before we get into some really sticky examples. What we're asking these questions based on this atom right here, wherever that proton was, and wherever the charge is now after the proton leaves, that's the atom that we're asking the questions about. Right, and we know that I'm telling you that up front, so that when we start asking about the factors that affect pKa, we're not talking about any other atoms in the molecule, just where the charge is. Right. So now here's the question. What is the hybridization state of oxygen in the conjugate base for propionic acid and in the conjugate base for phenylacetic acid? What is the hybridization state?
sp3.
It's sp3 for both, right? So there's no advantage there. Both atoms are sp3 hybridized, so there's no advantage. Because what happens is if there's one of these factors that's present for one acid and not the other, then that's an advantage for that acid. And that's a way to justify or explain why it's a better acid, right? So both sp3, can either of these do resonance?
Both can.
They both can do resonance. What's the pattern? What type of pattern do we see here? Is it an allylic anion, allylic cation? Like what pattern would this fall into, and I'll outline it. So this is the system. What do you think? What pattern does it follow?
Allylic anion.
It's an allylic anion, good. Right, so I can take this and do this. And I can do it on both of them, is that right? I can do resonance on both. Yes or no?
Yes.
All right, both can do resonance, so there's no advantage there. What about the, okay, let's go through the electronegativity and size real quick. Both atoms are oxygen. So is there going to be a difference in the electronegativity of oxygen in either one of those cases?
No.
No. What about the size? The size is the atomic radius of oxygen going to change because it's in propionic acid versus phenylacetic acid?
No.
No. So there's no advantage of size or electronegativity. But there's one other thing that could be an advantage, and that is induction. Right? Induction ask the question, are there any electronegative atoms or functional groups close to that charge? Right? If you look at the two molecules, right, the phenylacetic acid has an aromatic ring. Aromatic rings are really interesting because they can be, and depending on what the scenario is, they can be donors or they can be acceptors. But for the most part, an aromatic that's close by a negative charge is going to act as an acceptor. Right? Can somebody tell me what induction means? Anybody? What does it have to do with?
The arrows, right?
Which arrows? I think I'm reading your mind, but I don't want to misread it. Arrows in the sense of curved arrows moving electrons or dipole arrows.
Dipole arrows.
I knew it. I told you. I was reading your mind. So induction means that there can be a dipole set up because you have an electronegative atom or an electronegative functional group that can pull electron density towards itself. Right? Resonance is actually physically moving electrons from one atom to another. But induction is moving electron density. So in this case, the charge on oxygen for phenylacetic acid is stabilized through both resonance and induction because the ring is acting as an acceptor. And so it might not be a really strong dipole, but there's a bit of a dipole going this direction towards that ring, right? So induction is also a way to delocalize electrons. All of these factors have something to do with either delocalizing electrons or stabilizing them through electronegativity. Those are the two things that matter, right? You either stabilizing it through delocalization or through electronegativity. One of those two, but all of those factors have something to do with that. Questions about that? Let me write that down here. So the aromatic, it can delocalize electrons or electron density. Via induction. So this phenylacetic acid is stabilized by the conjugate base is stabilized by induction and resonance. That's how we explain the difference in acidity. Even if it's a small difference, like going from 4.28 to 4.87. Small difference, yes, on a molecular level, that's a lot, right? That's how we explain it, because the conjugate base is stabilized through both resonance and induction. Questions? Any questions? I'm gonna pause right here because I know that was a lot of information.
Oh wait, I have a question.
Go ahead. Don't hesitate. Go ahead.
If this were like, okay, so let's say we have a test and one of these questions were on there.
Mhm.
As far as like having like figuring out which one of the factors is the reason for their
Mhm.
difference, would we be given like the size of the atom and like
Well,
the
okay, so for the size, you can refer to a periodic table, right? So you'll have a periodic table. In general, the size of the atomic radius will increase from left to right and from top to bottom. So
okay, thank you.
If you're comparing like sulfur and oxygen, oxygen is above sulfur. So sulfur is going to have a larger atomic radius.
Okay.
Yep. Go ahead. You had another part to that question. I didn't mean to cut you off.
I think that was all. I was just asking if we will be given like the size, but you explained that we would just refer back to the periodic table to figure that out.
You're always going to have a periodic table either on the exam, or if it's open notes, you can use a periodic table from your book, from the internet, from wherever. Yeah, that's a good question though. Great question. Other questions about this example? So when we're talking about pKa, the rest of our discussion is really going to be about two things. It's going to be about the mechanism for proton transfer, which we're going to hammer and hammer and hammer. And then it's going to be about determining why one acid is more acidic than the other, right? Looking at the factors that stabilize the conjugate base of each acid. That's it. So let's do some more examples. There's another example. Let me see, hopefully it's on here. Yes, right here. I always skip this example, but we ain't skipping it today. We're gonna knock it out. We're gonna do number 6 and number 7. It says give a rationale for the observation that A is a stronger acid than B. All right. This is where my acidic proton is right here. This not this one. That's a trap, right? Remember, your acidic proton is normally going to be connected to a highly electronegative atom. And in this case, that proton can come off, but you need a really strong base to do it. But with the carboxylic acid proton, you don't need a strong base for that. You can use a really weak base, and you can deprotonate that. All right. So it's not the one down here. For now, you can pull that off. I think it was in one of the videos. It's called an alpha proton, but you need a really strong base to move that. All right, so we're not touching that. So these are the two protons that we're comparing right here. Right, and it asks to give a rationale. How do we explain acid and base strength in terms of, we don't know what the pKa's are, but we know what the given information is, that A is a better acid than B. How do we explain that? What do we start with to explain it? Do we explain it by just looking at the acid, or do we look at the conjugate base and see what we can do with that?
The conjugate base.
You always examine what the conjugate base looks like and then apply the model hires, right? To see which one of those factors is going to stabilize one conjugate base over the other. So let's do that. Let's take this. I'm gonna doctor this up a little bit. I'm just going to take that out. I don't want to have to redraw that. So I'm going to take this and I'm going to doctor it up. I'm going to put some electrons in. We're going to compare the two conjugate bases. Is that right? That okay? On a Friday? So these are my conjugate bases. Now, remember, this is my hybridization, induction, resonance, electronegativity, and size. What can we rule out? Right, there's no advantage to either one of those conjugate bases in terms of resonance, right? Because they can both do resonance. Is that right? Can I do that? We just saw this. Yes. So they can both do resonance, and the charge is on the same atom in both cases on oxygen. So electronegativity, size, and hybridization won't play a role, right? But look at the acid A compared to B. What do you think? Do you think those chlorines are going to have an effect on that charge? I'm trying to think of a good way to describe induction. So think about it like, think about the electrons, because normally we don't really get into the weeds of the electrons and the electron cloud that exists around the atom. But think of the electrons as a cloud of smoke around oxygen. If an electronegative atom or functional group is close by, it's like a vacuum. So if you turn that vacuum on around, and there's smoke around the oxygen in terms of electron density, what's going to happen to that smoke?
It's going to be pulled by the vacuum.
It's going to get pulled by the vacuum. Very good. So those chlorines are pretty electronegative. Yeah, they're not amazing, but they are pretty electronegative atoms, and you have two of them. And so what's going to happen in this case is you're going to get some induction going this way. Right, some polarization, and then that's going to cause that electron cloud to be delocalized, and that's good. Anytime you delocalize electrons, that's good. Right, when we talk about the cloud, that's what we mean when I say electron density. Right. What about on the other side? What happened? Where's the charge now relative to that group, that those two chlorines? Is it closer or is it further away?
This is for B, right?
You're talking about B now, yes. I'm sorry, I didn't make that clear. Yeah, for B.
It's further away now.
It's much further away, right? What happened is this carbon right here, this is a good little introduction to chirality, right? This carbon is what we call a stereocenter. And these two molecules, A and B, are what we call stereo isomers. They have the same molecular formula, same structure, but a different 3D orientation. Right, so you can see right here, the B, where the carbonyl is kind of pointed down, as opposed to A, where the carbonyl is pointed up. That matters, right? That's a 3D orientation. That doesn't change. So B and A are two different molecules, right? As a matter of fact, there's a specific type of stereoisomer that they are, right? And we'll call them enantiomers. They have a different 3D orientation. All right, so the question is now in B, with that oxygen, that negatively charged oxygen being further away from the group that's able to do induction, what do you think is going to happen? And this is how we explain the difference in acidity. What do you think is happening? Is the vacuum pulling as much smoke as it was if the smoke is further away from it?
That means it'll be less stable.
Yes, exactly. So here, the conjugate base is less stable because the inductive effect is lessened by the orientation of that oxygen. Right? So there's not as much induction there because the oxygen is in a different position. It's further away from the electronegative atoms, the functional groups that's there. So that acid is going to be weaker because of that. So get the rationale for the observation that A is stronger than B is very simple. In A, the charge on the conjugate base is stabilized by induction. In B, that induction is no longer possible because the charge is too far away from the atoms. Right, so that's how you would explain that. And it's not just A, it's the conjugate base of A. Right. All right, take a look at number 7. Somebody tell me, explain that to me.
Wouldn't A be stronger than B?
I agree with that. Why you say that? I agree.
Because the in A, the bromine, which like I think they're electronegative to an extent.
Mhm.
That's like those two, like they're closer in proximity to the electronegative oxygen.
Yes.
Or like when the base on the conjugate base electronegative oxygen, then and B when they're farther away.
Absolutely. That's exactly right. The bromines are closer to the atom that would end up being our conjugate base, right? So this would end up being O minus after you lose that proton. Over here be the same thing. Right. But again, you said a word that makes so much sense, proximity. The closer that group is, the same up top, it's the proximity changes because the orientation changed. The closer though that negative charge is to those electronegative atoms, the more of an inductive effect you're going to see. Right. So A is going to be stronger. And again, it's stabilized by induction. It kind of reminds me of the way I like to think about induction and resonance. I used to use an example like with resonance, since you're actually moving electrons, it's like somebody borrowing money. If they can't pay their rent, then they'll ask you for the money and you give it to them. That's resonance. You take your money or electrons, you swap it with somebody else. Induction is like they don't have the money for the rent, but they just don't show up. So you end up paying all the rent. So they got your money, but they didn't physically take it. Right. Another way to think about it is if you had a party and 3 people down from you are smoking and that smoke travels to you, that's induction. You're not smoking it, but you're feeling the effects. If they are 1 person away from you, then you're going to feel more of an effect, right? Because you're closer, you're more proximal to them. Same thing here. The the charge on the atom is going to feel more of an effect if the group, the electronegative atom or functional group is closer than it would if it was further away. The closer it is, the more stabilizing the effect is going to be. All right. Let's go up to any questions about that. We got plenty of time. Let's do these right here. It just says supply the arrows, right? Remember, for acid-base reaction, the arrows flow from the base to the proton. And then from where? So from the base to the proton is the first arrow. What's the second one? All right, we'll worry about it in a second. So let's look at what happened first. You can see over here that oxygen picked up, it had a proton transfer that happened, it picked up a proton. You can see that water lost a proton. Let me put the electrons back in. All right, so what happened? How do I show this proton transfer between the base, which is here, and the acid, which is here? Water can be both. It can be an acid or a base. How do I show that?
Would you draw a line from the H and that H2O right there, and then like I think you would draw a line from that and then connect it to one of the lone pairs or something on the base.
On the base. Okay, you are correct in that there's going to be an arrow between those two, but the direction matters, right? Let me clarify that real quick so we can have this, because we're going to talk a lot about this when we talk about nucleophiles and electrophiles. So everybody agrees that there's a dipole here. Yes, oxygen is 3.5, hydrogen is like 2.1, something like that. So it's a huge dipole. So hydrogen is partially positive. Oxygen is partially negative. These are the fundamental concepts that help us understand electron flow. So if I were to draw an arrow, I would never draw it this way, because what the end of the arrow tells me is that I'm moving electrons from that location to another location. What the tip of the arrow tells me is that I'm giving electrons to some other atom. Now, if we think about it, because this happens all the time when I teach this class. This is common. If I'm giving electrons to that oxygen, you think it's going to be, and I hate doing this, but you think it's going to be mad or happy in its current state with a negative charge and 3 lone pairs around it? Do you think it wants more electrons, or is it okay? Anybody? It doesn't matter. If you had 100 pounds of whatever in your backpack, 100 bricks in your backpack, and I brought you bricks, now real bricks, not other bricks, and I brought you 10 more bricks to put in there, are you gonna be happy or PO?
I would be mad.
Exactly. So atoms that are already electron rich, like this oxygen is electron rich, has a lot of electrons, so it's already rich. It does not want more electrons. So in this case, you're right, there's going to be a line between them, but the arrow is going to go from where the electrons are to where the electrons are not. So it's the electrons always go from what we call a source to a sink, right? So they move from an environment that's electron rich to an environment that's electron poor. So that oxygen is electron rich. The hydrogen here is electron poor. So that's how electrons flow. They always go to atoms that need them, as opposed to flowing from atoms that need them to atoms that don't need them. If that makes sense. Does that make sense?
Yes.
Yes, sir.
All right, so that's the first arrow for your base is always going to go towards the proton from a pair of electrons on your base. And then the other arrow that I was asking about is going to be here, right? I wish this bond was more clear, but let me see if I can doctor it up. The other arrow is going to be here, isn't it? When you pull off that proton, you break the bond between the proton and whatever atom is bonded to. And remember, we talked about Wednesday, when you break a bond like that, what type of bond cleavage is that? Anybody? Help me out. All these skills matter. So that's why I always try to bring them back up whenever I can. What type of bond cleavage is that? When I break that OH bond and give both electrons back to oxygen. Is it heterolytic? Can we talk about that Wednesday? All right, let's go back. I caught you off guard. That's okay. So remember on Wednesday, we talked about bond breaking and bond making. We said we break a bond. When we break a bond to an atom, like we do, like up here with AB, and I give both electrons back to one of those atoms, it's called heterolytic cleavage. So anytime we do an acid-base reaction, the OH bond or the whatever H bond, when I break that hydrogen bond by giving it some electrons from a base, it's when that bond breaks, it's going to be heterolytic. It's the same like this example down here. If C is the base and B is the proton, right? So C is attacking B. And because of that, the bond between A and B has to break and those electrons go back to A because A is more electronegative, if that makes sense. Stop me if it doesn't make sense or say something. Don't ever be afraid to interrupt if something doesn't make sense because you're paying for it. All right, so let's go back to here. All of these bond making and bond breaking processes with acids and bases are going to be bond making is going to be heterogenic, bond breaking, heterolytic. But I'm not going to put the terms in here yet because we're going to study that when we talk about nucleophiles and electrophiles, but you're going to already know it. But we're still going to study it. All right. So now we see that those two arrows that you see right there, you can put them in any acid-base reaction. It doesn't matter. Any acid-base reaction, you can put those two arrows in, the base to the proton, and then from the bond between the proton and whatever atom is bonded to, back to that atom. It never changes. All right. So over here we have cyclohexanol. I want somebody to look up the pKa for that. Go ahead and Google it. And we have the conjugate base, which is the hydroxide ion. And then while we're at it, somebody look up the pKa for water.
The pKa for cyclohexanol, right? It says 16.
It's 16. All right.
Yes.
What about water? Anybody got that?
14.
14. Good. All right. Why am I asking about the pKa's? Because now we can figure out the equilibrium. Which side is the I know it only asks about the arrows, but again, we're trying to build skill sets. So which side is going to be favored in that reaction? How do we know? How do we predict that? Is that right? Put the numbers on a seesaw. I know that's goofy. Some Ivy League professor is gonna see this video and be pissed off. They'll be angry. That is so juvenile, but it works. Which side is going to be favored? If you're on a seesaw and you weigh 10 pounds, preferably not ever, but maybe when you were born. But if you, let's say you weigh 120 and you got somebody on the other side that weighs 220, which way is that seesaw gonna tilt?
pKa
Towards
14.
the two.
Towards the person that's 220, is that right? So the pKa on the left is smaller than the pKa on the right. Which way is that gonna tilt? It's gonna tilt this way, isn't it? Is that right?
Yes.
So that means that the weaker acid, I said this the other day, I'm gonna repeat it. The weaker acid is always favored in a reaction, an acid-base reaction. You always want to go from a stronger acid to a weaker acid. So when I write the equilibrium arrows, they would look like that, right? Well, and that's showing that this side is favored, the product side. Right, questions about that? All right, we're out of time. We're gonna pick this up on Monday. So hopefully if you haven't watched the videos, watch them. If you don't like watching the videos, go on the Blackboard. In the reading section, it'll tell you in the objectives, it'll tell you exactly what section to read out of the book. If you want to look at some other videos on YouTube, feel free, but you got to do something. Because if you're not practicing and if you're not reading and studying outside of class, when you come to class, it's not going to make any sense to you. Hopefully, we're going to try to meet. I think everybody's done the survey by now. We're going to try to meet face-to-face for the people who did chose face-to-face on the survey. I think we're going to try to meet Wednesday of next week. I just need to make sure that this room is available on the 3rd floor. I had a room on the 1st floor, but another class is using it at 10. So I think we'll be able to get into room 304 on the 3rd. So preferably on Wednesday. I'll send a note out after our Monday class to remind you for those who want to come in person. All right, we're stopping here, and if there are no,
I have a question.
go ahead.
When is our next tutoring session?